Testing 1, 2, 3. All right. Testing 1, 2, 3. Testing 1, 2, 3. All right, I'll just wait until it comes on. I'll test it a little bit and then I'll start. Okay. All right, I'll just wait until it... Okay, it works. All right. So welcome to this lecture today, November the 12th, 2016. I have a few more things in chapter 3 to finish off, which I would like to do today. And then I'll give you homework. I have not yet given you homework for the last few sections of chapter 3, so I'd like to do that, probably 3 or so homework assignments. Okay, and then after that we'll have a quiz on the first chapter. But I'd like to keep these lectures going, so even if we're still working on homework for the last section, that's okay. I'll just continue going ahead with the subject material for this class, which will be the next chapter, chapter 4. Okay, so let me just finish off what I wanted to cover in chapter 3. So again, please let me know if you're here by giving something in the chat. Hello world or something. Okay. So now, anyway, this will be available online later. So last time we were looking at transformations of functions. I was looking at whether functions were even or odd. And yeah, I just gave the definition without any examples. So let me illustrate some examples of even and odd functions. Okay, so in general, if you're given a function, it's always helpful to graph it to see what it looks like. And once you graph it, it's usually quite easy to tell whether it's even or odd. Or neither. It could be neither as well. Okay, so let's try some simple functions first. I'll just test this sound again. Okay, so So some examples of even and odd functions. All right, so suppose here's 1. Suppose f of x is just the identity. So f of x equals x. Is that even or odd or neither? Okay, well the graph looks like this. It's 1, 1. That's y equals x. Okay, so is that even or odd? Or neither? Well, what you do is you plug in. If it's even, the condition is that f of x is equal to f of minus x. So the minus sign appears just with the x inside. If it's odd, then the relation is f of x is equal to minus f of minus x. So there's a minus sign inside and also a minus sign outside. Okay, so if we plug minus x into this expression, then we get minus x, right? Just replacing x by minus x everywhere. And that's equal to the original function with a minus sign in front. so we get this formula, which is equivalent to this one. So this can be written either way. The minus sign outside over here or outside over here. Okay, so this is an odd function. So another way you can see it is that every point that is on the graph over on this side for x positive, namely say 1, 1, has a counterpart point which is over on the other side, obtained by changing the signs of both x and y. So you have -1, -1 over there. Okay. So that's an odd function. An example, let's say, of an even function, how about the constant 1? So f of x is equal to the constant 1. Constant function. Or it could be c. Any constant. So there's the graph. Now we can see that any point over here namely 1, 1, has a counterpart obtained by reflection through the y-axis, -1, 1. All right? So remember what I said last time. The even functions are reflection symmetric with respect to reflection about the y-axis, and the odd functions are symmetric with respect to reflections about the origin. In other words, the distance from this point to the origin is the same as the distance of this point to the origin, and they're along the same line, but on opposite sides of from the origin, along that line. And meanwhile, this line, this point is the reflection of this point, and vice versa about the y-axis. Okay, so let's verify using the formula. If you take any minus x, plug it into the function, you get 1, but that's the same as the function at x, because the function is constant, has the same value, always 1. And so this is satisfied. So we see in both cases that it's an even function. Okay, notice for the odd function, f of 0, x is in the domain, and so we expect f of 0 to be 0, and it is. Whereas here, the even function doesn't necessarily have to have any condition on f of 0. In this case, it's 1, but it could be any value. Okay. How about f of x is equal to x squared. Okay, so these are part of the tool. These are parts of the tool. These are the toolkit functions I'm going through a little bit. Here, it's the parabola, and you can see it's going to be an even function again, because of the symmetry with respect to the y-axis. Okay. All right. And again, you verify that by plugging it minus x into the equation. Minus x, that whole thing gets squared. You put the minus x inside the square, inside the brackets. You square everything, and then you get the same as x squared, which is the original function. So this is even. not s, the absolute value function. Okay, so that looks like 1, 2, 3, 1, 2, 3, minus 1, minus 2, minus 3. All right, again, you can see the symmetry with respect to just the y-axis. Oh, and notice it's not these functions are either even or odd so far, not both. So for the identity that's odd but not even, because you can see it's not going to be symmetric if you reflect about the y-axis. That's this line here, just this line, the identity. It's not going to give you this, it's not going to overlap with itself if you reflected about the y-axis. And similarly, the constant function, if it's 1, then if you reflected about the origin, you'll get the negative 1 function as a constant. And that's not the same. It doesn't overlap. What value of the constant will give you an odd function as well? So it could be odd and even. It's always even, at least even. But it also is odd if what? If the constant is 0. So f of x equals 0, the constant 0, is odd as well, since you're going about the origin when you reflect about the y-axis as well. Okay, so that's kind of an exceptional case. In fact, when a function is odd, is both odd and even, then it's easy to show or prove that f of x is equal to minus x and it's equal to minus f of minus x. So because it's a minus sign here, you solve this part and f of minus x is 0. For all x. So in other words, also for f of x. So it's the constant function 0 if it's both odd and even. That's just an aside. Okay, so this function is obviously not 0, so it can only be one or the other of odd and even. And this looks like it's symmetric with respect to the y-axis, so that looks like it should be even. So we just have to check this equation. Is it true? And then you see that, yes, it's true because the absolute value of minus x is the same as the absolute value of x. Because one way you can think of the absolute value function is that it is a measure of the distance from the point x along the real axis to the origin. So just look at the real axis only. Right? If you pick a point x along the real axis, then the distance from the origin is 0, and likewise the distance from minus x to the origin is also, the distance from x to 0 is x, if x is positive, which is shown here. And the distance from minus x to the origin, again, it's just the same, if x is positive. I've shown x positive here. Okay, so another way is piecewise defined. Case. Okay, this is piecewise defined way of defining the absolute value of x. Right? If I stick in minus x, well, what is it? It's minus x if minus x is positive, right? I just stick it minus x everywhere where I see the x in this definition. And it's plus x if minus x is negative. But this is equivalent to, actually it could be 0 as well. It's the same if it's 0. So this is equivalent to x is less than or equal to 0. And this is equivalent to x is positive. And so you can see that these are the two cases above, except just in a different order. Okay, so it's the same as this. All right. Okay. So it's an even function. All right. And you can see, you can check all of the examples. So usually it's just a matter of plugging in all these toolkit examples. It's a matter of plugging in minus x into the function and seeing whether it changes sign or not. It gets you back the original function. So the inverse function is going to be odd. You can see it also by reflection through the origin. The inverse square, like this, reflection symmetric about the y-axis, so that's even. The function y is equal to x cubed is odd. If you plug in minus x into that, then you get minus x cubed. Okay, so you can see that any odd power of x is going to be odd. So this is one reason that these functions are called odd and even. The odd powers are 1, 3, 5, 7, 9. And you guessed it, the even power of x is also an even function. So constant, that's x to the power 0, x squared, x fourth, and so on. If you put a minus x in there and then take an even power, then it gets you back the original function without a change of sign. Okay, however, a function like this, so it's the sum of an even power and an odd power, or like this, an odd power and an even power. These are neither even nor odd. Okay, there's no symmetry about the y-axis or about the origin for these functions. And you can check that f of minus x is equal to 1 minus x. So that doesn't change sign, but that does. And that's not equal to 1 plus x. Neither is it equal to minus 1. Minus everything 1 plus x. Okay. Now let's do some examples of transformations of functions. Oh, yeah. I also wanted to finish off the section on stretching functions, stretching and shrinking, or stretching and compressing. Okay, so a vertical stretch of a function is another function which you start from the original function, and this is the absolute value function that we're starting with. Let's get the scale right. It's not quite. Okay. There's the original function. This is minus 1, 1, 1. X-axis and y-axis. Okay, remember when you graph, notice I'm always trying to make the graph as clear as possible. So when you draw a graph, try to draw straight horizontal and vertical lines for the axes. Label the axes x and y. Label some of the points, equal spaces between points, please, and equal hash marks, and also put some labels. And it's always helpful to put some illustrative points on the graph. Make sure that it looks clear. Okay, it's helpful to use graph paper if you have some. So vertical stretching is, what I want to do is, for each y value, I want to multiply that y value by a factor, by a constant factor. In this case, the factor will be 2. Okay, so I claim this is what will give me a stretched graph in the vertical direction. So you can see that x does not, if x is 0, then it doesn't change the value of the function. So 2 times 0 is 0. So just as before for this function. So that's also a point on the second graph. If x is equal to 1, or minus 1, and I get 2 for both, for this new function. Okay, so it's up here. And I can see that any other point will be the same as this point, but doubled. Okay. So the resulting graph will also be a straight line, but this straight line will have a slope which is absolute value of that each slope is 2, so it's twice as much as it was before. Okay, so this the slopes originally are 1 and minus 1 for these components of the graph, and here it's 2 and minus 2. So that's a stretch by a factor of 2 in the y direction, or in the vertical direction. Similarly, if you take y is equal to the absolute value of x over 2, then that's going to be a shrinking, or a compression, in the vertical direction by a factor of 1/2. Okay, so you have to get a value of x equals 2, and then that will give you 1. And minus 2 will also give you 1. So it will look like this and like this. Okay, the graphs are all symmetric still with respect to reflection about the y-axis. In other words, they're all still even functions, but they'll just be stretched in the y direction or compressed in the y direction, all by the same factor. So each value of y gets multiplied by the same factor. Okay, so this is a compression by a factor in the vertical direction by a factor of 1/2. Okay, so how about horizontal stretch and compression? Should say compression here. Okay, so for that, okay, if we do that, then we're going to be stretching in this direction. So let's start with the original function. Now this function is okay, stretch in the y direction. Stretch in the y direction is going to be equivalent to a stretch in the horizontal direction, or the x direction. But first, let's see how it works in the y direction. So I suspect if I start with y is equal to the absolute value of x, I start with the absolute value of x, and I want to stretch it in the horizontal direction. Then I want to arrive at a function that looks like this, right? Because that's what I got here. All the y values will be, half as much as they are for the original function. But that's equivalent to saying that fix the y value and I multiply the x value by 2. So I want to go from this point, fix the y value, and we'll go over here. So if I go down by a factor, that's changing y, leaving x the same. But if I fix y and then increase x, well, it's going to give me a different point. But if I look at the collection of all the points and all the stretching in the x direction, then I'll get the same line as before. Okay, so I expect to get the same answer here for the function. I also get this side stretched away from the origin along the x-axis. Right? So I claim that what I have to do is replace x with x divided by that stretching factor, 2. Okay, so this works in a similar way as the shifting did. I kind of do the reverse operation on x. So it's not going to stretch. You think you might have to put a 2 there, but it's not that way. You start with a new value of x, all right, the stretched value, and you divide by 2 to get the unstretched value. Right? The old value of x is 1 for this point. The new value will be 2. So I want to go from 2 back to 1, and then evaluate the original function, which will be 1. Okay. So this will be equivalent to the original expression, y. It's because the absolute value of x over 2, it's just the the distance of the point x over 2 from the origin, but that's equal to the absolute value of x from the origin, the distance of x from the origin, divided by 2. So the distance is shrunk. You can take the factors out as long as you take the positive factor. Okay, you don't change the overall sign of the absolute value function. Okay, so this is always correct. And likewise, compression in the vertical direction, compression is going to give so this is compression by a factor 1/2. This is going to be the same as 2 absolute value of x. So if I compress in, I'm going to be taking, say, this point here, 2, 2. And I keep the y value the same, and I divide the x value by 2, and so I go inside like this. I push the graph towards the inside, towards the y-axis. Likewise on the other side, here I have minus 2, 2, and that goes to minus 1, 2. Roughly speaking, it's like that. Okay, so these are the two functions that are the stretching in the horizontal direction and compression in the horizontal direction along the x-axis, or along the horizontal axis. Okay. I'm just showing a few points here, try to make that clear. All right. How about x squared? Phi is equal to x squared. Okay, so now let me try to stretch in the vertical direction. So again, if I want to stretch by a factor of 2 in the vertical direction, then I multiply by 2 in front of the whole expression. So I take y and the old value of y, which is x squared, and I multiply that simply by 2. That will give me a new y value, which is twice the old one. So 1 minus 1, and here we get 2. All right, and then at 2 we get 2 squared is 4. Actually, it's way up here. We'll go all the way up to 8, so it's up here somewhere. 2, 4, 6, 8. Okay, so these are this. We get a sharper parabola, or a narrower parabola. Okay. Through the points. Like so. All right. So that's the graph of the new function. A compression in the vertical direction. So you simply take that compression factor 1/2 and you multiply it by the original function. All right, so you have 1 will give you 1/2. Minus 1 will also give you half. 2 will give you 2. Minus 2 will also give you 2. So you'll get this more gentle curve. And the original curve is somewhere in between that. So you've stretched it. Let's show the original curve just to be clear here. Okay, so the original curve is y equals x squared, and you've stretched it to y is equal to 2x squared, and you've compressed it in the vertical direction to get y is equal to 1/2 x squared. Now if you stretch in the x direction, then let's stretch by a factor of 2 in the x direction. Okay, so the point 1 will give you stretched to 2. And minus 2. Minus 1 will be stretched to minus 2. And 2 will be stretched to 4. I'm talking about the x values only. Okay. So the original function looks like this. The x value is 1, y value is 1 here. X value is 2, y is 4. And likewise on the other side. That's the original function. Then the stretched function in the horizontal direction okay, you take 1 and you stretch it, it goes to 2. You take the x value at this point, it's 2, and you stretch it to 4. So it looks like this. And minus 1 goes to minus 2, minus 2 goes to minus 4. Okay, so again, it's a more gentle curve. It should be symmetric. Smooth. Notice my parabolas are always, there's no sharp point at the vertex. It's always a smooth curve there. Here this should go through the origin, the same point. All right. So what does it look like? Again, you take your x and you replace it by x over 2 inside the function. So I square everything. So this is actually x squared over 4. All right. So this graph is the same as a graph that's compressed. It's the compression of y is equal to x squared by a factor of 1 over 4 in the vertical direction. That's equivalent to, that's my symbol for equivalent to, compression, so vertical compression by a factor 1/4. Okay, it makes sense? Because, okay, so you take this point, say, then the x coordinate is 1, sorry, yeah, x coordinate is 2, sorry, the y coordinate is 4. And you compress in the y direction by a factor of 4, so y goes from 4 down to 1. And that is exactly on this second curve that I've already drawn. So the point 2, 1 is already on that curve. Okay, likewise, if I go to, well, the next even value will be 4. 4 squared will be 16. So in the original curve, I'll get 16. Then I divide by 4 and I get 4 again. So that again is correct. All right, so it's a compression even more than this one is. This is only about a factor of 1/2. This is a compression of an even smaller factor. Okay, so you can see that how some of these toolkit functions give you, if you do a vertical scaling, it will be equivalent to some horizontal scaling or stretching, or we call this in general scaling. All right. Okay, so other toolkit functions that you might encounter are y is equal to 1 over x. All right, so now if I stretch in, let's say I compress in the horizontal direction, by a factor of 1/2. So compression is always referring to a factor that's less than 1 in absolute value. A stretching is referring to a factor that's always greater than 1 in absolute value. So if I compress in the horizontal direction by a factor of 1/2, then I have to take x and divide by 1 over 2. Right, so this big line means you do that bracket last. So these are like brackets. You do this bracket first, and you take x divided by that. That's equivalent to 1 over 2x. Okay, so that's what I would get. How do you see this in the graph? Let's see, so at point 1, the graph is 1. 1 over 1 is 1. At 2, it's 1/2. At 1/2, it's 2. And so on. 3, it's 1/3. At 1/3, it's 3. As x increases, y decreases, and vice versa. So this is 2, 1/2, 1, 1, and this is 1/2, 2. And then you get the negative part of it as well. As it never reaches the x or the y axes. We would say that the x and y axes are asymptotes of this function. Okay, so if we stretch this by a factor of 1/2, or sorry, compress it by a factor of 1/2 in the horizontal direction, that means we're taking values over here, we're taking points over here, and we're making the x component half as much and keeping the y component the same. So x goes from 2 down to 1. Okay, so I should get the same value of y if I take, instead of 2, which will give me y equals 1/2 for the original equation, I'll take 1 here. And indeed I get the same value of y, 1/2. Okay, so at this point, this point is on the graph. Right, for this equation over here, whereas over here, it's 1/1/2 is on the graph. Of this equation. So everything gets shrunk in that way. So this point goes to 1/2, so that's 1/2, 1/2, and it's going to be 1/4. So the graph is just simply closer to the origin everywhere like this. And similarly, these points get shifted in like this. Oh, sorry, that should be over here. That should be 1/2 over there. That's right, -2, -1/2, like that. So that gets shifted over here. All right, this point gets shifted over here. This point gets shifted, so it's like that. All right. This is equivalent to, in the y direction, what is equivalent to? A compression of 1/2 or a stretching of 2. It's equal to compression of 1/2 in the y direction. Or in the vertical direction. So again, if you look at the original function, what overall value do I have to multiply the original function to get the new function? Then it's going to be the factor of 1/2. Okay, so that's why this is true. All right, and you can see from the graph as well. From the graph, you can see that all the y values have to be made less for each corresponding x value. Okay. So now let's do combinations of these operations. There's some exercises in the book which I refer to here. So problems from the text. Okay. So this is section 3.5, the part on transformations. Let me just check that. Okay. So these are the exercises, yeah, and at the end of section 3.5. Number 7. So the question here is, write a formula for the function obtained when the graph is shifted as described. F of x is equal to the absolute value of x. And this is shifted down 3 units and to the right 1 unit. Okay, shifted vertically down by 3 units, down, up and down are vertical. To the right and left, those are horizontal. To the right by 1 unit. Okay, so you don't have to necessarily graph. You understand the rules now. So to do these, it's independent of which way you do the shifting if you do both a vertical and a horizontal shift. But we'll see later that if you stretch and shift, then the order does matter there. Okay, so you want to shift down by 3 units. then you simply take the absolute value of x and then subtract 3. That's shifting down. So that's one step. And then the next step is you shift to the right by 1 unit. So that means you take whatever value of x and you take x minus 1. So you'll increase the value of x. The new value of x will be increased from the old value, but when you use this formula to evaluate, you will plug in the old value of x to get the same value of y as you had over here. Meanwhile, that value of y was the previous value of y shifted down by 3. Okay, so this is the final answer after shifting. So you can basically write them down in both orders, in both steps in one. And either order that you do those steps will give you the same answer. Right. So if you do the shifting to the right by 1, you do it that way, then you would get x minus 1 first, absolute value of x minus 1, and then if you shift down by 3, you would get simply subtract 3 from the previous step. Same answer. Okay, but there are other cases where you might get a different answer if you perform the transformations in a different order. So here's an example where the order matters. Answer does not depend on the order here. Here the order matters. Okay, so I'll take this as a starting function, and I will shift up by 1 and stretch in the vertical direction by 2 to get a factor which is different from 1. Okay, so what does that look like? And show that that's different from doing it in reverse order. If I stretch by a factor of 2 first, and then shift up by 1, I'll show you that that's a different function. Okay, this is not in the text, by the way. I think I'm just making this up, but I wanted to show you this particular case. Okay, so in the first case, so I want to do the first one, this one first, and then number 2 second. And then I want to do 2 first, stretch in the vertical by 2 in the vertical direction, and then do 1, shift up by 1. And then I want to show that these will result in different functions. Okay, so the first function, so let me illustrate this step by step. The original function, we start with the absolute value function. Okay, so we have this shape. Now we shift it up by 1. Okay, so all the values get shifted up like this. So 0 goes to 1, 1 goes to 2, 2 goes to 3, and so on. Okay. So that's, as long as you're not straight. Okay, so this is 1. This is 2. Yeah, this is 0, 0, 1, 1, and this gets shifted to 0, 1, 1, 2. Right, so that's the new function. So I get it by adding 1 to all the y values of the old function. So I shift vertically by 1, and then I stretch vertically by 2, by a factor of 2. Okay, so now each y value gets multiplied by the same factor 2. So 1 gets multiplied by 2, and I get 2. X stays the same. 2 gets multiplied by 2, and I get 4. 1, 2, 3, 4. Likewise, minus 2. At minus 1, the value of y is 2, and I get multiplied. That gets multiplied by 2, and I get 4. Okay, and so this whole line, and likewise, if I go to 2, that goes up to 3. And 3 doubled gives me 6, so I have to go 2, 4, 5, 6. So that gets up to here, and this likewise gets up to here. So I want to take the whole previous function and multiply it by a factor of 2. Because I have to put the whole expression in brackets and multiply by 2. So it's actually 2 to the value of x plus 2. Okay, now let's do it the other way. I'm not labeling, but sorry. Okay. Now let's do it by first stretching by a vertical factor of 2, starting again from function y is equal to the absolute value of x. Looks like that. Here's a point 1, 1, minus 1, 1. Okay. That's my scale here. Not too bad, I guess. A little bit could be better. All right, x and y. So now I first stretch in the vertical direction. So 0 gives me 0. These are y values only. Y equals 0 gives me 0, so I stay there. Y equals 1 gets stretched over to 2. Here's y equals 1, it gets stretched to 2 again. 2 gets stretched to 4. So the graph looks like this. Okay, so that's the first thing. So it's actually still, the vertex is still going through the origin. This point is on the graph. Now I shift it up by 1. So each y value gets incremented by 1. So I go from 0 to 1. Here I go from 2 to 3. Again, 2 to 3. 4 to 5, 4 to 5. So here's my, oops, sorry, I did that wrong. Should be parallel to the original graph, each line. Okay. So just the same shape. The original graph is like this. This second graph is slightly different shape. It's just shrunk in the y direction, so it's scaled, one axis is scaled differently than the other. So so it definitely looks different from the original graph. And then the third graph is the shift of the second graph, upwards by 1. So notice, compared to the original graph, it's moved up, the origin is moved up by 1 from the original graph, as well as the shrinking, or as well as the stretching in the y direction. But here, in this case, the first case, it's moved up by 2. Okay, so they are different. The results of changing the order of these two operations results in different functions. Okay, let's write this out. This one is, okay, I'll write this one out first. 2 absolute value of x. And here I just add 1 to this function on the outside. So no brackets, right, involved. I add 1 just totally to the outside of this function. So you can see numerically how they're different, not equal to each other. Okay. Now the way you can say this is that in the first case you do the shifting first, and then you stretch the function in the vertical direction. So you're actually including the shift along when you do the stretching. You're actually stretching the shift. Or to say it, in other words, the shift is stretched here. Whereas over here, you're doing the stretch first, and then the shift. So the shift is unstretched. It's only half as much as it was over here. Excuse me. All right, so that's something that one should be careful with when doing combinations of these transformations that you could have. It could depend on the order in which you do them. So please watch out for that. Okay. Let's do a few more. So 18, number 18 and section 3.5. It says we're given y is equal to f of x minus 2. So f is some function. They don't specify what it is, but they give this form. Y is equal to f in brackets of x minus 2 and then plus 3. And now you're asked to describe how the graph of the function is a transformation of the graph of the original function f. Describe how the graph of the function is a transformation of the original function f. Okay. So in words. All right, so you can see that you're doing, it doesn't matter what the order is, but at first you are doing, let's say, a shift in the horizontal direction. Because you're subtracting 2 from x, it's a shift to the right. So you shift horizontally, or in the x direction, to the right by 2 units. And you are shifting upward, so in the y direction, by 3 units. So that's basically the answer. That's all you have to say. Okay, determine the intervals on which the function is increasing and decreasing. Okay, so now they are in the book, they're incorporating the ideas of increasing and decreasing. So this is a review of one of the previous sections of this chapter. So this is number 20. Determine the interval or intervals on which function is increasing or decreasing. F of x is equal to 4 x plus 1 squared minus 5. All right, so this is a function, this is a quadratic function that has already been put in a completed square form. And in this form, this is easy now to describe this quadratic function in terms of the toolkit function f of x is equal to x squared. So one of our simple basic functions. So in terms of our basic toolkit function x squared, what is this function? Okay, so you basically have a shift in the x direction by -1. So that's to the left now, okay, because we have a plus sign here. And so the origin, okay, this is where the vertex is for this function. Here the vertex is going to be -1, -5. Because, and remember I could write it like this as well. This is my general function, and remember we saw before that this h and k, that's the vertex of the parabola. And the a was some scaling factor. Before I just wrote it in, but now we'll be able to see what it actually represents. It's going to be a scaling in the y direction by a factor 4. So it'll be stretching in the y direction by a factor 4. Okay, so if you just get an idea for the graph of this function, then it will be easy to find the intervals in which it is increasing or decreasing. So we have -1 and 1, 2, 3, 4, 5, this, -5. So here's where the vertex is. Okay, and now if we go to a neighboring point, it's helpful to draw a table. So -1 gives me, this evaluates to 0, and then I get -5, correct? And then 0, this will give me 1 times 4 is, 4 minus 5 is -1. And the other one, symmetric to that, it's all the way up here, is at -2. And that evaluates again to 1, and it's going to also be -1. Okay, so it's a sharp parabola here. Oops. Something like that. Try to draw it clear, like, sort of generally increasing on both sides. All right, the stretching factor is 4. How do we see that? Okay, the stretching, if we do stretching and shifting in the same direction, either vertical or horizontal, here we're doing both. Both are being done in the vertical direction. So we're stretching in the vertical direction, and then we're shifting in the vertical direction. Okay, so you have to be careful of the order. So if you describe it as first stretching in the vertical direction, yeah, first let's shift in the horizontal direction. So we shift this function by 1 in to the left, and then we get this function. Okay? So it'll be sitting up here somewhere like this. All right, that's y is equal to x plus 1 quantity squared. All right, then we want to do what? We want to stretch first in the vertical direction by a factor of 4. That will stretch this up, make it sharper like this. Okay, so that's this function here. And then we want to shift downward by 5. So first stretch and then shift. And then we don't have to worry about stretching the shift as well if we do the shift last. Okay, so then we get this final function by shifting this skinnier graph all the way down to -5. And that's it, then we're done. Okay, so now it should be easy to read off where the function is increasing or decreasing. Well, you look at where the vertex is. To the left of the vertex, the function is going down towards the vertex, so we always think of what the value of y is doing as x is increasing. So the x is increasing from -infinity to this point, x, which is -1. So in terms of intervals along the x-axis, this is the interval on which the function is decreasing. Okay. Now in the book, it gives another notation. It usually, well, it's not. It's definitely different meaning. It gives this open bracket. You could also do that. Okay. On that interval, it's decreasing. I like to include that point because of the definition, which says that given any 2 points on the interval, if f of x1 is less than f of x2, when x1 is less than x2, then the function is increasing, for example. Okay, then that would allow the endpoint to be included. But in the textbook, they leave out the point where the function might be actually instantaneously horizontal. But technically, everywhere including that point, if you go away from that point, then the function will be greater in x1. So for this one, x1 is 2. Look at the 2 pairs. X1 is less than x2, and f of x1 is greater than f of x2. Okay, so that means it's decreasing along this interval. And so this one, or either way of saying it, is fine with me. And going the other way, -1, except if you're given these choices, you'd probably only be given one of these choices if it's a homework question. So I might give it in this form, so just be careful about that. So, and then -1 to infinity is where it's increasing. Okay. Now in some function, there's another thing I might have missed. When is a function constant on an interval? A function f is constant on an interval AB if f of x is equal to a constant everywhere for all x in that interval. Okay, so f of x1 is equal to f of x2 for small, x1, x2 in AB. In general, they can be different, right? Okay, so it'll look like this. So you might have a piecewise defined function where it's increasing here, it's constant here, and it's decreasing here. Okay. Next question, 71. In the same section, 3.5. H of x is equal to minus 2 plus 3, sorry. Minus 2 absolute value of x minus 3 in brackets inside this absolute value. And then on the outside, plus 3. And the question is, describe how it is a function of a toolkit function, then sketch. Or how it is a transformation of a toolkit function. So now first we want to do the shift in a horizontal direction. So this tells you that it's a shift to the right by 3 units. Okay, that's independent. We can do that at any point here. So the order of doing this could be done first, or one of the middle ones or last, even. But the other steps you have to do in this order. So you start with the toolkit function that you want to start out with is going to be y is the absolute value of x. So that's our starting point. And you shift that to the right by 3 units. You get absolute value of x minus 3. And then you do these following operations. You want to transform, to multiply by a factor of 2. So that's a stretching in the vertical direction. By a factor of 2. And then you get y is equal to absolute 2 times the absolute value of x minus 3. Okay, so how it's looking is, here's the graph of y is equal to absolute value of x, and you shift it to the right by 3. Like this. That's right. 2, 3. Something wrong here. Oh yeah, I did it wrong. Here's the origin here. Okay. Helps to get a few representative points so you can get this right. So that's a shift by 3 in the horizontal direction, and then you multiply by a factor of 2 everywhere, so you then stretch it. 1 gives you 2, so it looks like this. 4 here, 4 up here. Okay, so that's this one. And now you want to do what? Multiply by minus 1. So that's going to be a reflection about which axis? Well, it's going to change all of the y values to minus y and leave x unchanged. So it will take you down to this part here. So there's actually be a reflection about the x-axis. And so you'll go down like this. 1, 2, 1, 2. And then finally you shift upward by 3. So we're not, if you did the shift first and then multiplied by -1, then you would reflect the shift as well, and it wouldn't be upwards by 3, it would be downwards by 3. So shift upward by 3. So this whole thing goes up by 3, so it's 1, 2, 3 up here. And this goes down like this. Okay, so that's this final one. So all at once, you can do everything at once. First you find, so to speak, the vertex where that is. You can see easily that it's where x equals 3 and y equals 3. 1, 2, 3. 1, 2, 3. So here's where the vertex will be. See it from that graph as well. And then it will open downward because it's a minus sign in front, and it'll be stretched in the y direction by a factor of 2 because of that factor of 2. So instead of going, if you go to the right by, if you go to the left by 1, you don't go down 1, you go down by 2, so it's going to be at 2, 1. And this one will be symmetric with respect to that, so this will be 4, 1. And then it will keep on going like that. So you can actually draw this just by using 3 points. And yeah, so you can see those 3 points on this graph as well. Okay, so that's how to do it all at once. You have the shift in both x and y directions. They will give you the location of the vertex. The new location of the vertex is going to be at 3, 3. And the stretching will be shown as how fast you draw or how much the slopes are of each line. The slopes will be 2 and -2, and whether it's opening upward or downward is determined by the sign there, which is negative. So that would mean it's opening downward. Okay. So that's how it's described by the transformations of toolkit functions, of a toolkit function. So it's a series, I should say, series of transformations of a toolkit function. Then sketch it. Okay. There are just 2 sections I want to deal with. This has to do with the absolute value function. There is a section 3.6 in the book which deals with more on absolute value functions. So I'll just do some examples from that section. They want you to, for example, there's some important skills to learn in this section. For example, one of them is to given the graph of an absolute value function, or a function involving absolute values, find the corresponding equation. So that's an important one. So if we have the graph that looks like this is 2, that's 1, that's 0. So the slope is +1. Here, m is -1. So what will that be? What is the corresponding function that you would write down? Okay, well you just take the original toolkit function absolute value of x and you shift it to the right by 1, so that results in putting x -1 in there, and then you shift down by 1. in the y direction. Okay, so this is the result of that, those two steps. And you can also check your result. Is 0, 0? It looks like it should be in the result of evaluating x equals 0 should be 0. Is that true? We plug in x equals 0 here, you get absolute value minus 1. That's 1. And 1 minus 1 is 0. So that's correct. And if you put in 1 minus 1, then again you get the correct, if you put in x equals 1, you do get minus 1. So that's correct as well. So that's the origin. Oops, y is equal to minus 1. Finally, if you put in x equals 2, you get 2 minus 1, which is 1. 1 minus 1 is, again, 0. Okay, so those are both 3 points are correct. So that checks our formula. How about this one? One, two. Okay, so what is the corresponding function for this one in terms of the absolute value function? Okay, so first you shift the origin so that it is at 2 minus 2. So you shift it to the right by 2 and then down by 2. So you get those two parts. But you also have to scale it. So it's a stretching in the y direction by a factor of 2 because the slopes are 2 instead of 1 in absolute value. Okay, so I claim that that is what will give me the resulting function. Just put a factor of 2 there. So first you shift in the x direction, then you scale by a factor of 2 in the y direction, and then you shift down by 2 in the y direction. So I'm leaving the shift until last. Okay, and so let's check these numbers. Let's try 1 and 3. X equals 1 gives me y is equal to 2, and I plug in 1 and I get absolute value minus 1, which is 1. 1 times 2 is 2. 2 minus 2 is 0. And that's correct. Okay, good. The other one is 3. Let's check that 3 is also 0. Get the 3 gives me 0 for y. So I get 2 times, again, 3 minus 2 absolute value, minus 2, so that's 1 again, and so it's 2 minus 2, which is 0. Okay? So I've checked those 2 points. And likewise, 2 gives me minus 2, so that's the origin. So checking 3 points usually is enough to make certain that this is a correct graph. This is a correct function describing that graph. Now there's an example also involving absolute value functions to find the 0 of a function involving absolute values. So let's just do that one. Find zeros of f of x is equal to absolute value 4x plus 3 minus 5. So we want to equate this. You want to find the set of all solutions such that absolute value 4x plus 3 minus 5 is equal to 0. All right, so how do I solve this equation? So I can't easily just eliminate the absolute value signs. I have to keep them there. But what I can do, what I know is that if I have an expression absolute value of x equals a constant, and that constant will have to be bigger than 0. Otherwise, there are no solutions, right? Then x can be plus or minus c. So there are two possible solutions. So it's like taking the square root, except there's no square root here. Okay. So in this case, you have 4x plus 5. The absolute value is equal to 5. That's positive. Okay. So I want to find all the solutions. So I can take away the absolute value as long as I allow for both, for this positive value or for that to be negative, for this side to be equal to the negative of that. Okay, and now this, when you solve it, gives you 4x is equal to 0 or x equals 0. And this, when you solve it, gives you 4x equals minus 10, x equals minus, divide by 4 on both sides, I get minus 5 over 2. Okay, so this should be the solution set. And then let's check it. We plug in 0 into the original equation. Oh, sorry, 3. Yeah, sorry, it was supposed to be 3. Okay, so we'll get slightly different values here. 4x plus 3 is equal to 5, or 4x plus 3 is equal to minus 5. So here we'll get 4x is equal to, subtract 3, and I get 2. And I get 1/2 here. And here I get minus 5 minus 3 is minus 8. X is equal to minus 2. So we get 1/2 minus 2 for the solutions. Okay, so that's the virtue of checking. As soon as I looked at the original equation, I could see they were both going to be wrong. So I realized my mistake, and I just corrected it all the way through. So let's see if it works. 4 times 1/2 plus 3, that's going to be 2 plus 3. Do that inside first, because that's like a bracket. So 2 plus 3 is 5. Absolute value of 5 is 5. So I get 5 minus 5, which is 0. So that is a solution of it's one of the zeros of this equation. And finally, f of minus 2 is 4 times minus 2 is going to be minus 8 plus 3, and that's going to be minus 5 in brackets, and then I take the absolute value, that's plus 5. 5 minus 5 is, again, 0. Okay. So let's sketch this. What does that look like? All right, so it's let's look at the inside here. So the overall function will be shifted down by minus 5. The vertex will be where? Okay, if I write it in this form, I can take the factor of 4 outside. I divide each number in here by 4. At the same time, and then I'll get the same thing. Okay, so I could write it like that. That means it's shifted to the left by, or sorry, shifted to the left by 3 over 4. So it's going to be minus 3 over 4 is the x-coordinate of the vertex, and then minus 5 is all the way down here. Okay. And the factor in front is going to be the factor of the slope. This is going to be the slope of the positive part. And so it's 1, 2, 3 is going to get me to the origin. 1, 2, 3, 4. Okay. If I go the other way, then I will get This will give me a minus 1 when I reach this point. So it's going to be 1, 2, 3, 4, minus 2. It's going to look like that. So the zeros are, it's what x equals 1/2 and x equals minus 2. That's where the graph intersects the x-axis, or that's where the y values of the graph are both 0. The only place. Okay, so that illustrates the solution set as the intersection of this horizontal line y equals 0 with the graph itself. Okay. So again, I'll work on giving you exercises and homework by email, and also on Maple. I'll let you know when that's ready. And but basically, this should be the end of chapter 3. So anyway, let me just check, are there any, okay, somebody's here, good. Just checking if people were responding. Yes, they have. Farzana's here, good. All right, so she asks, sir, can you say what is the next lecture? I want to get preparation for that. So the next lecture I would like to work on is starting in chapter 4. I would like to also talk about cost and revenue. Cost, revenue, profit, possibly for the next lecture, but in any case, I would like to start with the section or chapter 4, section 4.1 for next time. Okay. As well as this cost function stuff. Okay, so with that, thanks for watching again, and hope to see you next time. The next lecture will be on Monday, on the 14th of November. Okay, so Chudofis, have a good day. Shabbat Chush.